Good afternoon, everyone. So continue our discussion from last time with universal gravitation. And we ended on this checkpoint question. We force the gravitational attraction between the Earth and the Sun, right? When we show that this force is G m1, m2 over distance squared. So this is the attraction between two objects, and the force is the same because one of the force is acting on A by object B, and the other force is acting on object B by object A. These are the action and reaction pairs. According to Newton's third law, these forces are always equal in magnitude, right, and opposite in direction. So the force should be equal. Now the follow-up question to this checkpoint is what about the acceleration that is acting on the two objects, one being the Earth, the other being the Sun. As you can see that you probably have already noticed, the force is acting on the object, F equals ma. Now, if you have a more smaller mass, you're gonna have a bigger acceleration if you have an equal amount of force acting on it, right? So even though the force between Earth and the Sun is the same, because the Sun is so much more massive, the acceleration on the Sun is so much smaller. And you see the effect on the Sun is so minimal. It's the Earth that's orbiting around the Sun, and the Sun is barely being affected by that gravitational attraction. Right, so how does the acceleration of the Earth compare to the acceleration of the Sun? Then it's the Sun's acceleration is so much smaller than the acceleration of the Earth, right? And the correct answer is this one. Now let's look at to use this expression to answer some questions. If the distance to the moon were doubled, then the force of attraction between Earth and the moon would be, how would that change? And recall, again, we are looking at the universal gravitation. F is equal to G. This is the gravitational constant, m1, m2 over the distance squared. So I'm going to open up the code and let you vote on this one. All right, 10 more seconds. This should be pretty quick. Okay, all right, let's take a look in the last minute vote. All right, very good. We can see this 1/4, the choice is the correct answer. Very good. Now, I'm glad that we all know that agree at least it's A or B, so that we know that the force should be reduced, right? Make the distance longer, the weaker the attraction, right? You're further away from each other. But it is 1/4 because it's a distance squared, right? If distance becomes 2d squared, you can see it's 1/4d squared. So it's 1/4 of what you had before, the force you had before. Okay? So A is correct, very good. All right. So the slightly more interesting question. Now we have two different objects that is exerting a gravitational pull on the Earth. So here we're looking at one planet M and another planet twice of the mass. And the planet M is at distance d away, but the 2M is at 2 distance away. They're both exerting a force on the Earth, right? They're both giving the force a gravitational attraction. Distance in general square. Okay, so you can see that what is the net force acting on Earth? Okay. There are 5 different arrows. Which one relatively represent the correct direction of the vector? That is the total gravitational force on Earth. This one, I will let you discuss it for a minute or two, and after you come back, you can. Okay, 1 second. Okay, 10 more seconds. Go for 10 more seconds. All right, any last minute vote? If not, I'm gonna go ahead and close this. Let's take a look. All right. We know that one of these arrows, 2 of these arrows is apparently not correct, right? A and D. Because if that's the force, that means the force is purely downward or the force is purely to the right. But the Earth is being pulled by M and 2M at the same time, right? So two of the forces. So you superposition vector addition for the forces, the total force should be the sum of them. So now exactly how do they sum up? You can calculate each of the force by using the gravitational formula for universal gravitation, right? The force between Earth and one of the planet is G constant times the mass of one of the objects. The mass of the other object is the Earth, so the mass of the Earth divided by the distance between them, d squared. Now, the other force is 2m. One of the masses is 2m. Again, is between 2m and the Earth's mass of the Earth, 2d squared. So this one is end up to be 1/2 of F1, right? Because you can see mass doubles, distance 2d, so 1/4. Then this is 2, it's 1/2 force of F. So when you have two vectors, this one is longer and this one is shorter. And when they add up, you will have a total direction is in this sort of direction, right? So it's not C and D. B is correct. Okay, and very good job. B is correct. C seems to be in the diagonal direction, seem to indicate these two forces are equal in magnitude, right? So it's relatively a sort of 45 degrees angle is where C was indicating. But these two are not equal. One is longer, one is shorter. Now, if I reverse the setup, right, if this is 2m and at 2d, this is m at 1d, then you would choose choice D because now the other force, the horizontal force, is longer. Okay, so this one is longer, this one's shorter, so they add up to be something like this. Okay, B is correct. Now let's look at a few checkpoint questions you have already answered online. We're talking about how when we're standing on the surface of the Earth, right? The little g, 9.8 meters per second, can be calculated using the universal gravitation equation. Simply taking the distance between you and the Earth is the Earth's radius for that, if you're on the surface of the Earth. So if we, on the other way around, what if we want to look at the acceleration that the Earth experienced due to your gravitational pull? Which one of these is correct? Okay. So we have already done this one. So to get the acceleration acting on any object, you say the force is equal to m times acceleration. So here I'm using big M to represent the mass of the Earth, right, times the acceleration of the Earth. This is what we want to calculate. What is this acceleration, right? Not is what your acceleration is, but what the Earth's acceleration. Okay, and we know the gravitational pull between the two objects, that is the Earth and you, is G, mass of you, times the mass of the Earth, divided by the distance between them. Here we use the distance is, if you think of the Earth being all the mass concentrated at the center of the mass, at the center of the Earth, and the person is here, right? The distance is really just going to be the radius, relatively the radius of the Earth. That's the distance between these two objects. So D is equal to R. And then let's calculate A. So set this equal to that. And you can see you can cancel the capital M from both sides of your equation, right? And the acceleration, the Earth, is G, mass of U, divided by V squared, okay? So this is the answer. Sorry, which is described by choice D. Okay? And this is a very small quantity, very small acceleration. There are some numbers that if you wish to refer You could always, you don't have to memorize these when you need to use it. You can always check it. G is a very small constant. Mass of the Earth is very big, and radius of the Earth is also very big. In fact, if we want to calculate what is the acceleration on U, right? In the checkpoint question, we calculate what is the acceleration on the Earth. But what if the acceleration is on U? Then you use m equals ma, acceleration on U. The force is the same, G little m, big M, divided by the radius of the Earth squared. This is the gravitational acceleration acting on U. So you can calculate the acceleration on U is G times M over R squared. And you can plug in these numbers. You can plug in G, you can plug in the mass of the Earth and the radius of the Earth. So this number should relatively equal to 9.8 meters per second squared. This is what we know, we're familiar with this, is the little g, the gravitational acceleration, right, at the surface of the Earth. Now, because with the Newtonian mechanics, we are dealing with all of the problems we solve are relatively around the close to the surface of the Earth. So the gravitational acceleration is always around 9.8. That's why we just use little g to represent it. And we say the force of gravity is m times little g. We didn't bother to use this equation, okay? Because this is enough to describe the everyday problems that we have. But if you were to go to outer space, then obviously you have to go back to the universal gravitational equation. I also want to talk a little bit about gravitational potential energy. Okay. 1 second. Remember, earlier when we do conservation of energy, we will say, now if you take Earth into your system, we will talk about, for example, from here to here, so an object going from a lower place to a higher place. We will say the system is your object plus Earth. And from here to here, the gravitational potential energy of the system increased, right? From lower place to higher place. Now the same process, you can describe it using a different system. If you take Earth away from your system, right, from initial place to the final place, you can talk about this using the work done by gravity, because now Earth is not part of your system, which means Earth is an external force that can do work on your system. So from here to here, what is the work done by gravity? From here to here, let's say I have lifted the object up by a height h. What is the work done by gravity? What would you tell me? Work done by gravity is equal to, I still remember?
Mass times gravity times height.
Yeah, m times g times h, mgh, very good. And from here to here, does gravity do positive work or negative if you're going up? If I'm lifting something up, is the work done by gravity positive or negative? It's negative, very good, because displacement and force are the opposite direction. Very good. Gravity is always pointing down, but you're going up, right? You can see your displacement is pointing upward. So work is F dot into delta X or delta R. They're in opposite directions, you have a negative sign. So this is negative mgh, okay? So that's why a lot of times people say the amount of the work done by gravity is the negative of the increase in gravitational potential energy. The MGH can be interpreted two different ways. One is potential energy, one is work done by gravity. Depending on your choice of the system. Hopefully I have explained that clear enough. So if you can see that here, my the work done is negative, and the potential energy has a positive change, increase. Okay. So a lot of times people say, if you want to calculate one, you can calculate the other and simply throw in a minus sign. So that's a lot of times you say, you want to know the change of potential energy, the process, you just say that is equal to the negative of the work done, the force. Okay. Now we're going to do the same thing, but now instead of looking at the force is mg, we have a more universal expression that is g m1 m2 over r squared. Okay, so we're going to use that expression to derive what is the potential energy of an object at a distance r away from a planet Earth or any other planet. So we're going to do this. So now let's look at this process. Here we have our Earth right here. Okay. And here we have an object. You can move the object from infinity far away to where the object is at a distance r away from the center of the Earth. This is r. Okay. So this process. So move the object from infinity to at a distance r away from the center of the Earth. Okay. Now, what is the work done by gravity during the process? So the work done, now first of all, you want to think about whether that work is positive or negative. You can see that from infinity to r, displacement is going into closer to Earth. And also we know that the object is being pulled by the Earth. The force of attraction of G is also pointing in that direction because of attraction. So displacement and force is in the same direction. I know I'm looking forward to a positive work. So I know that whatever, how do I set up my limit? F dot into the L to calculate work from lower limit to upper limit. I know eventually I need to get a positive number. Okay. So I do my integration. Knowing that it is positive, you can here, you could just simply focus on the magnitude of that. Right? You can just say, well, I already know it's positive. So whatever the magnitude it is going to be the amount of work. So what is a force? The force is this formula, G M of the object, capital M of the Earth divided by distance squared. So here R, I'm representing R using a general, this R is really just a general variable describing how far the object is away from Earth. Okay, now dl, you can see that you can choose to evaluate this process by saying my object going directly into the Earth in the r hat direction. R hat for it's really just this radial component is called r hat. So going directly in without zigzag. You're not really going this way. You're going directly in. Okay, so my path is simply dr, right? You can choose to choose whichever path you want to take, and I'm simply going to choose the direct path, okay, dr. And you have your integration limits, which is from r to infinity, and your lower bound to upper bound. So to describe the work done in this process. Now we can go ahead and calculate it. So this one gives me negative GMM over 1 over R, okay, from a random distance R to another upper limit to infinity. So this is the result of this integration. If you plug in the limits, infinity minus GMM at R. You can see this is 0, and my result is GMM over R. This is the work done. Okay? So this is the work done from point A to point B. And we're going to invoke this relationship. You can view the same process by describing the change of potential energy. If you have done positive work, then your potential energy must decrease. You have done negative work. So from here to here, something going up, gravity does negative work, then your potential energy increase. See that? So here I've done positive work, then my potential energy must decrease from point A to B. So from A to B, my potential energy must decrease, which means the change in potential energy is the potential energy at location B minus the potential energy at location A must equal to the negative of the work done, which is negative G and M over R. Okay. So point B, where is point B? Point B is at a distance R away. And where is point A? Point A is at infinity away. So the change of potential energy we have derived is negative M, capital M over R. So you can see that we can define our reference point to be anywhere. Remember with Earth, with potential energy, we say you can set your sea level to have 0 potential energy, or you can set your desk to have 0 potential energy, right? It's all about the reference. And here we set our reference point to be at infinity. We say when you're infinite far away, your potential energy is 0. Now that makes your potential energy at a distance, random distance away is negative Gm capital M over R. Okay. So potential energy of a system when it's within the gravitational pull of a planet is always negative. Because we had set 0 to be at infinity y, right? And this has to be lower than that reference. So that's where you have this expression is this gravitational potential energy is a function of R, and it can be calculated by negative Gm1, m2 over distance R. Okay. The force, though, just to compare with the force equation, is Gm1, m2 over R squared. Okay. They have different units, and this is your reference point. Okay, now let's look at a question. It's asking what is the speed required for an object, which is m1, to orbit around the Earth at a radius r away from the center of the Earth, like a satellite. So what is the speed required for an object to be able to go around the Earth? And to go ahead and let you discuss for a little while, and then we can So the object is going around, so this must be circular motion. You must have centripetal acceleration, right? Think about how you might want to incorporate that into answering this question. Okay, 10 more seconds. Let's go for 10 more seconds. All right, let me go ahead and close it. So this is our results. We're going to calculate the speed required for an object to be able to stay in this orbit, right, going around. And what is the speed required? Now we view this as a centripetal circular motion. For an object to remain in circular motion, you need a centripetal acceleration. So what force is providing the centripetal acceleration right now? If I have a rope and I attach a object to one end and I swing it around, and I would say the centripetal force is provided by the tension of the rope. In this case, the satellite is going around the Earth. What force is providing that centripetal force that we need for the satellite? It's gravity, yes. So it's to be more universal, it's the universal gravitational force between the Earth and the object, that attraction. Very good. So if this is the Earth, this is the object, it's the attraction between the Earth and the object, and that is the force that's providing the centripetal force that we need for such a motion. When we say centripetal force, that force is not a new force. It's named after its effect. Right? So at different scenarios, you have different forces will play the role of a centripetal force. In this case, it's gravitational, the gravitational attraction, the gravitational force. And we already know how to calculate this force, right? It's G, mass of the object, mass of the Earth, divided by the distance between the object and the Earth. Here it tells me is radius r away, r squared. This is equal to F equals an A Newton's second law, right? This is the force applied that should equal to mass times acceleration. So how is acceleration? How do you calculate the acceleration A centripetal? You still remember?
V squared over R.
Yes, very good. V squared over R, and we can calculate the V. Right? It's what the question is asking us to do right now. You can see you have a mass one here on both sides. We can cancel. We can cancel one of the R, leaving another R. So V squared is equal to G, mass of the Earth, divided by R. So V is equal to the square root of G, mass of the Earth, divided by R. So that one is the correct choice. Okay. All right. I think a lot of you voted for a different answer. Probably you recalled one of the answer choices looks like some other velocity or that you have seen in your pre-lecture. The second question is, what is the minimum speed required for an object to escape Earth? So what does it mean to escape Earth? Well, the satellite is orbiting around the Earth. In that scenario, do you think the satellite has escaped Earth or is still within the influence of Earth's gravitational pull? So when you orbit around Earth, have you escaped yet? No, you haven't. Very good. So what does it mean to have escaped? Means, as the hint says, that your gravitational potential energy becomes zero. Okay? When you're under the influence of Earth's gravitational pull, you have this potential energy. As you're escaped, that is you become zero, and you can view yourself as to be infinite far away. That you is zero. So this Earth's gravitational pull no longer affects you, so you have escaped. Okay. So what is the minimum speed required? There's another condition. The minimum speed refers to, well, if I barely escape something, meaning that once I reach that point, I just happen to stop, right? That is the minimum you need. If your speed is more than that, when you reach that point, you still got some momentum, you continue going. But the minimum is once you reach this point, you also have stopped. Okay, so that tells you, I'm going to give you a hint. You're going to use conservation of energy approach. You're going to choose a initial moment and a final moment. Initial moment is when you are on the Earth's surface and you say, I'm shooting a rocket into space. I want this rocket to escape Earth, right? So you're shooting this rocket at Earth's surface. That's your initial state that have some kind of velocity. And you want to calculate what is this velocity required. So that eventually, finally, final moment, this object has escaped Earth and its u is 0. And also, it just happens it stopped at the moment. It tells you something about the kinetic energy. Okay? So try to think about how you might use conservation of the energy approach to calculate the u like here. All right, so that's the hint I want to give, and then we can have a little bit discussion before we come back to it. Okay, let's go for 10 more seconds if you haven't voted already. All right, let's take a look. So how do we calculate the escape velocity? Okay, very good. So we're looking at the system of the object plus Earth. We're looking at the final state being the object has already escaped Earth. So we're saying at that moment you have zero potential energy and barely escaped, meaning at that moment you happen to just have stopped. Meaning you have barely just escaped, but you don't have any more speed to go anywhere else. You barely just escaped. So it's potential energy zero, kinetic energy zero. So final energy is zero, right at that point. Initial energy is when you're at the Earth's surface. So at Earth's surface, you have two types of energy. You have your kinetic, you have your potential, and we derived what is the potential. U is negative G M1 M2 over R, right? Okay, so it's negative G object and the object and the Earth, right, over R. When you're at the surface of the Earth, the distance between the object and the Earth is radius R of the Earth. This has to be equal to input and output. There's really no other forces involved. There's no input or output. Okay, so from this you realize I can calculate the velocity required. Minimum velocity required right here is equal to Gm m1 m of the Earth over R. So we derive V is 2 Gm of the Earth over R and square root of that. Okay, so very good. C is indeed the correct answer. It's twice as much as the earlier we're looking at orbiting around the Earth. Here we're looking at escaping Earth. So you need a much bigger velocity to have escaped the Earth gravitational field.
Professor, I think your screen is frozen. Oh.
Oh, sorry. Let me go ahead and reshare. Sorry. So you probably have missed where I did the derivation. Final energy is zero. Initial energy is when you're at the Earth's surface, right? You have kinetic energy, that's 1/2 mv squared. You have the gravitational potential energy, which is negative Gm m1 m of the Earth over R. And there's no input output zero. So that's why how I derived this result, right? Okay, so C is the correct answer. So this is what we call escape velocity. When you're at any planet, if you want to calculate the escape velocity, you use this formula. So if you're at Earth, you want to escape Earth, you use the mass of the Earth. If you want to escape some other planet, you do the mass of the other planet. That's called escape velocity. Okay? So you can see the two general strategies we used, whether something happening or interesting going on when you're near a planet, is whether you are orbiting around, you can simply calculate that using F equals ma using the centrifugal acceleration. Or if you have escaped, we use conservation of energy to have solved for this velocity. Okay? So these two typical type of problems you will come across. Now the rest of them, it may look like a lot of math, but I want to tell you that gravitation is actually one of the easier chapters because there's not too much problem solving going on. It's a lot of times it's just plugging and chugging numbers, right? When you're giving this expression, plugging, chugging numbers, later on when we do Kepler's laws, right, you will have to look at the period of an object orbiting around a planet, and that's a lot of plug and chug. So we are dealing with a lot of astronomical numbers. That's why these numbers are big, but it's not really difficult. Usually a lot of the questions in gravitation is really just a simple step. Okay, so I just wanted to encourage you not to be too discouraged from the big numbers you will see. Okay, a couple checkpoints you have already done. First question, part 1. Where would the weight of an explorer be greater? Okay. So you have all these names, but really what matters is the numbers. Okay. Is at the summit, which is at a distance about 6,384 kilometers away from the Earth center, or if you're at another place, which is at a smaller distance away from the center, or if you're at the surface of the Earth. If you're at the surface of the Earth, the radius is 6378 kilometers. So that is the radius of the Earth. Okay. Now you can see that which one the explorer have a bigger weight. Where does the weight come from? You stand on the scale, you weigh yourself, you see a number, and that number show up because Earth is pulling on you, right? So really, it's asking where would the Earth be pulling on you with the biggest amount, hardest? Which force is biggest? So that is a question, is what it's asking. And you know already how to calculate the force, right? Is this expression that's showing up over and over again. So it's the same you, the same person. So your mass would not change. And the mass of the Earth doesn't change. What changes is how far you're away from the Earth. So if you're at a shorter distance away from the Earth, you're going to get a bigger gravitational force. If you're at a longer distance away from the Earth, you're going to get a bigger gravitational force. So if you weigh yourself at the closest distance away, which is B, because this is the smallest number, right? Smaller than this and this, you're going to get the bigger weight. So it's really just comparing which one have a smaller distance, R. So that's also why if you weigh yourself at different location of the Earth, your scale will read differently. Because you can see different places will give you a different gravitational pull. If you weigh yourself on the moon, you get an even smaller number, way smaller, right? Because of the gravitational pull of the moon is much weaker. But you can see your mass hasn't changed. You are still the same person. What changes is the little g, right? When we say 9.8 meters per second square, is really an overall average. If you measure this little g on the Earth's equator, or if you go to the North Pole, you're going to measure different g. But on average, we say it's 9.8. Okay, so what changes is your weight, but not your mass. So it's not going to be a effortless weight loss plan if you simply weigh yourself at different locations, right? You say, oh, I've lost 5 pounds, but not really. Your mass is still the same. It's just the Earth is pulling you with different amounts. Okay, the second part to this question. Okay, now the explorer visited these 3 different places, and she raised her hands and she reached each of the places and raised her hands to a height h. Where would the change in gravitational potential energy of her hand be greater? Okay, this one will require a little bit more calculation. I'm gonna add a page so we can look at the process. So we're looking at the change of your gravitational potential energy of the hand. But you're already at the hand is already at a distance away from the center of the Earth, and when you raise it, you're taking it to an even different height away from the Earth's center of the Earth. So exactly how do we compare? Okay, so let's say this is the center of the Earth. This is where you were. 0.1 and you raise your hand, you're at 0.2. Okay, so this is R1 and this is R2. It is equal to R1 plus H. Okay, so if we're looking at the change in potential energy, change is delta U. That means change of potential energy. 0.2 minus 0.1. Right? This is where your hand was. This is where your hand is. What is the change? Okay. So to calculate potential energy at 0.2, you use this equation, right? U is equal to negative Gm1 m2 over R. So at 0.2 is negative Gm1 m2 over R2. And U1 is negative Gm1 m2 over R1. It's really the distance is different. Okay. So to put them together is Gm1 m2, 1 over R1 minus 1 over R2. Right, this become positive. So 1 over R1 minus 1 over R2. Okay. Now R1 and R2 are related, right? Because if you raise your hand, the hand has gone up by a height h. So I can represent R2 with R1 plus this h. Let's say your hand is at 2 meters above the ground right now. I raise it and maybe at 250 centimeters above the ground or something like that. Okay, so it really comes down to comparing this. So just one more little step. It's R1 plus H. The numerator becomes R1 plus H minus R1. This becomes just H, right? And the numerator becomes H. So let's compare at different locations. So how high your hand is at different locations, right? When you are at this place, your hand originally is at 6,384 kilometers away from the Earth center. When you are going to a different place, your hand is at a closer distance away from the center. You can see how different R1 will affect the change differently. So if R1 is smaller, it's on the denominator, this change will be bigger. You see that? Because everything else is the same. So which means if you raise your hand at a lower place, smaller, a lower mountain, then you're going to have a bigger change in the potential energy. All viewed from this result. R1 plus H on the denominator. Okay. So by looking at this, well, again, this one is the closest one, and this one is going to have the biggest change. But this does require a little bit of a calculation, a manipulation of your symbols. Okay, so B is correct answer. All right, now shifting gears a little bit, I want to briefly touch on Kepler's laws, but don't worry too much about Kepler's laws. Mostly what would you do there is we're given an equation, we often simply just plug in numbers. It's not too much problem solving there. Okay, who is Kepler? Kepler is a mathematician, physicist, also astronomer. He's a founder of celestial mechanics and made observation of the planet's movement. Okay. And we also know Isaac Newton. Who is him? It's a person who claims that if you see further, it's by standing on the shoulder of the giants. So he was also referring to Kepler to be one of the giants where he based off his work on. He established laws of motion. You already know Newton's the 3 laws, first, second, third. Newton also had a great contribution of discover universal gravitation. And the universal gravitation can explain Kepler's observation. So Kepler's laws is more of a like a phenomenological law. It's not fundamental. It doesn't tell you mechanically why the planet is moving this way. Kepler only make observations saying, based on my observation of the stars, it seems that they're moving this way. That doesn't tell you why. But Newton's law of gravitation is more fundamental. It's showing you the attraction is proportional to the mass and inversely proportional to the distance squared, right? But he based off his work on Kepler's observation. Isaac Newton also is a mathematician who developed the calculus, method of calculus. Okay, so this Kepler also has 3 laws based on his observation. First law is the observation of the planetary orbits are ellipses, where the sun is at one of the focal point of the circle. There are 2 focal points. The sun seems to be one of them. It's not a perfect circle, it's an ellipse. The second law, Kepler's second law, is to show that the equal amount of times the planets sweep out equal areas. Okay, based on observation. Can't really explain why, but that's just how he observes. Kepler's third law is giving a formula to calculate the time it takes for an object to go all the way around the period. It is proportional to the semi-major axis cubed. So if you're looking at the ellipse, you have 2 semi-major axes. One is in vertical direction, we call that B, and in horizontal direction, we call that A. And this is showing you that the time it takes to go all the way around is proportional to this distance A. Okay? And if you're talking about the sun's attraction, it's always inversely proportional to the sun. Okay. So the other checkpoint question you have seen is really just plugging and chugging the numbers. You could have just taken the equation and dump all the numbers in there. You can solve all the problem that way. However, I want to be able to show you that a lot of times all we need to care is the order of magnitudes. We want to be able to do these problems a little bit simpler without having to plug in a lot of numbers in my calculator. So exactly how are we going to do that? Let's, for example, look at the part 1 of this question. It presents you 2 different kind of orbits. One is the moon is going around the Earth, okay? The other is Charon going around Pluto. So in both cases, the one that is the center of the attraction is the Earth or the Pluto, right? By calculating the period for the satellite, one is the moon, one is the Charon. So which one do they have a bigger, a longer period? Now you can simply just calculate it, right? Whatever number they give you, you can plug it into this equation. I think I don't need to say more there because we all can just plug it into our calculator and solve it. But these numbers are really big, 10 to the order of 20 or even more. Right, so plugging those into your calculator might be quite difficult. So I want to show you there's a simple way to compare them. We know that they're the difference are probably orders of magnitudes away. So we don't care about these numbers. We just care about, okay, this is 10 to the order of 24, and that is 10 to the order of 25. So the other one is bigger. That's all we care about. So we're going to do an order of magnitude estimate on these numbers. So T really depends on the difference between these 2 types of orbits is the semi-major axis of rotation and the mass of the central body. One is the Earth, one is the Pluto. So we just wanted to compare, okay? I'm going to look at the order of magnitude of A cubed, and I'm going to look at the order of magnitude of M, because the rest of them, they're equal. To see the ratio of A cubed over M, which one is bigger. Let's look at the Earth and the Moon. Okay, it tells us the A that we needed is 370,000 kilometers. Okay. If you use SI units, you can change that further into meters. So, okay, so order of magnitude, 1, 2, 3, 4, 5, right? This is 3.78 times 10 to the order of 5 kilometers. This is also a common technique we do and do calculation. We don't enter everything into our calculator here. We just enter, if you need the specific number, you just enter 3.78 into your calculator. This is 1, 2, 3, 4, 5. But it's kilometers, which is 1,000 meters. So 10 to the 5th, 10 to the 3rd, you get 10 to the 8th, right? So A is on the order of 10 to the 8th meters. So A cubed is on the order of 10 to the 24 meter cubed. Okay, so the order of magnitude here is 10 to the 24, and the mass of the Earth is 10 to the 24, which is given. Okay, so that ratio gives us 1. The t squared is proportional to 1. You see, this is much simpler and quicker to calculate. You don't have to input everything. And now let's do the other pair, the Charon and Pluto. That distance is this distance. Again, let's count how many order of magnitude that is. Okay, so that's 1, 2, 3, 4, right? 1.96 times 10 to the 4th kilometers. And kilometers is 10 to the 3rd power of meters, 1,000 meters. So overall, that's 10 to the 7 meters. And if you make cubed, that's 10 to the order of 3 times 7 is 21 meters. And the mass of the central body for that orbit is the Pluto, which is 10 to the 22. Okay, again, that ratio from A cubed over mass is 1 over 10 is 0.1. This ratio is 1. This ratio is 0.1. So you can see, obviously, we know which one is bigger, right? That the Earth, the moon's orbit, has a longer period. The answer is A. Okay. All right, hopefully I haven't lost you. There are just a lot of numbers, but I want to show that a lot of times we can just do an order of magnitude estimate. The second part of this question is exactly the same. We are doing an order of magnitude estimate. Let's ask him, which object exhibit the smallest escape velocity? And we derive the escape velocity, right? Is this formula. So if you're talking about escaping the Earth, you're going to use the mass of the Earth and the radius of the Earth. If you're talking about escaping some other planet like Pluto, you're going to use the mass of the Pluto and the radius of the Pluto. Really, you're looking at the ratio mass over R, which one is bigger? So which one is smaller gives you the answer, the smallest escape velocity. So which ratio is the smallest? So there are 4 different planets. Escaping each of them will give you a different escape velocity, right? For example, the Earth is order of magnitude 10 to the 24, that is the mass. The radius of the Earth, be very careful, 6,000 kilometers, okay? That is 6 times 3, 7, 8 times 10 to the 3rd kilometers, and this is 10 to the 3rd meters. If you wanted to estimate everything using the SI units, so this is to the order of 10 to the 6, okay? So if you look at this ratio, mass is 10 to the 24, radius is 10 to the power of 6. This gives you 10 to the power of 18. Velocity of the escape velocity at the Earth is proportional to 10s of the order of magnitude of 18. And do the same thing for the rest of them. Okay. Now, this one is a 16. And why is that? You say this isn't this 10 to the 24, but this is much smaller. You wanted to make the number leading up to it to be comparable. So I will rewrite this using 7.3 times 10 to the power of What should I put here? So if I move this back 2, this becomes 7.3, and 10 to the power of 24 becomes 10 to the power of what? How much?
22.
Very good. Okay. So this is 10 to the 22 divided by, this is still on the order of magnitude 10 to the 6, okay? Just like the Earth. And that's 10 to the order of 16, so smaller. You do the same thing for Pluto, you end up with the same. You do Charon, it's the smallest, only 10 to the power of 14. So you can see that this is a technique not only is useful in universal gravitation, but when you see if I plug in my numbers elsewhere, I do this strategy. I put the tens all somewhere else and I don't throw it into my calculator. I only calculate the rest of the constants. So it's much simpler and you can avoid making mistakes this way. Okay. All right. There are 2 examples left, but we don't have time to go through it. Also, it's not very difficult. As I said, it's really just repeatedly plugging and chugging numbers. So it's not too much problem solving going on. So I wouldn't worry too much about this particular section, right? You just need to know the equation and the meaning of that equation and know how to use it. So for example, this example is asking what is the period of our orbital motion about the center of the galaxy in Earth years. So the challenging part probably has to do with unit conversion. How do you convert different units? So plugging numbers is not hard. You can plug in the numbers t squared. What's that here? Numbers are all given. But I want to show you just a little bit how to do the unit conversion. In astrophysics, a lot of times we're talking about light year. Probably still remember at the beginning of the course, we say light year is a distance, a length quantity, is how much light travels in a year. Okay, it's a distance. Distance is speed times time. This is the speed of light. This is how much time it is in a year, right? So 1 year, there are 365 days in a year, and there are 24 hours in a day, and there are 1 hour. In 1 hour, there are 60 minutes. In 1 minute, there are 60 seconds. So there are this much second in a year. That's how you do the unit conversion, and that is 3 times 10 to the 7 seconds. So you can change the light year, what they give you, to SI units, which is meters. And again, when you get the result in seconds, you can convert it back to years, if you like, doing the exactly opposite, right? Whatever seconds, how much seconds, you're saying divided by 60, that's how much minutes. Another divided by another 60, that's how much hours. Divided by 24, that's how much days. Divided by 365, that gives you how many years. You wanted to talk about your period in terms of 500 years or something like that. It's just a unit conversion. So example 1 and 2, I have the solution here. You can see plugging in the equations is easy. Just want to be a little bit more careful in converting your units. And also when you plug in into your calculator, for example, you're leaving the tens, the order of magnitudes away from the calculator. You don't touch it, you plug in the rest of it. For example, here I will plug in 4 times pi squared times 2.55 cubed into my calculator. On my notes, I will have 10 to the order of 60. This one I do not plug in, I leave it, okay? All right, so that's all I have for you today. We have finished our discussion on universal gravitation. And starting next week, we will do simple harmonic oscillation. Have a good rest of the week. I'll see you guys next week, okay?
Thank you, Professor. Have a good rest of the week.
Thank you. You too.
Thank you, Professor.
Thank you. Bye-bye.